So our second speaker in the session is Professor Samy from Virginia Commonwealth University. So he's a distinguished professor there of chemistry. And he's going to be telling us about how MOF catalysts are going to be the next generation of catalytic materials, I think. So welcome you to the stage. Thank you very much.
Well, thank you very much. It's really a pleasure to be here. This is my 14th time to speak at the conference. And thank you, Tony. And of course, I organized the first 4 conferences, but now the conference keeps getting better and better every year. It never reached a plateau, so it keeps going up and up. So thanks to Tony and Natalie for such great work. So today, I want to talk to you about catalysis using MOFs. And I'm not going to say much about MOFs because the next speaker is going to tell you everything you need to know, and sometimes also if you don't need to know about MOFs. So the plan here is I want to cover just some catalytic applications using MOFs. So, and before I start, of course, this meeting is in the Arab world, and we have a lot of students from Arab countries, and you should know and appreciate and recognize that 3 of the pioneers of MOFs are Arab scientists, chemists. And one of them is going to speak in a few minutes. So the plan for my talk is I want to give examples of using MOFs first as a catalyst support and what kind of modifications and tuning of catalytic properties you can use by changing the support, not the catalyst itself. And this will be done through catalytic upgrading reactions of biomass using palladium catalysts. But the MOFs will be the support catalyst. I'll give 3 examples of that. And the finally, second part, I will talk about MOFs as a catalyst. So this is cobalt-copper bimetallic catalyst that can actually surpass the very famous and well-known platinum-carbon catalyst for oxygen reduction reaction. So the first group of reactions, this is about upgrading materials for biofuels upgrading. And the reaction here is vanillin, which you can see here, which is a typical model system for lignin. And it's 2 steps hydrogenation to form a vanillin alcohol, and then follows by hydrogenolysis to form methoxy-methyl phenol. This is actually the product, the desired product. And you can think of this, if you have a good catalyst, as even 1 step going from vanillin directly to the methyl phenol. So this is important because this conversion allows you to make phenol, of course, which can be used as a biofuel in one way. And it also can go to a lot of manufacture of materials based on phenol manufacturers. So the first system we used to study this reaction as a support was a cerium-MOF. Cerium-MOF is developed where you have all the cerium atoms are coordinated with open sites for oxygen binding, and it can be made from a reaction of cerium nitrate and trimesic acid, as you can see here, in DMF. This MOF actually has a very low surface area, so it's maybe 60 or 70 meters square per gram, so it's not that useful, but there is a way that we can increase the activity and the tuning, the properties of this MOF by incorporating in a hybrid structure, as I will show you next slide. So this is first the MOF that was synthesized, the cerium MOF. It forms needles structures, and you can load palladium by many ways, nanoparticles, that's the catalyst on this MOF. And of course, the XRD shows no changes from incorporation of palladium on this MOF, indicating that there is no changes in the structures that are taking place. The approach that we used to increase the activity of this MOF support is to incorporate a layer of reduced graphene oxide in a hybrid structure. So the idea here is to synthesize the cerium-MOF at the same time in the presence of graphene oxide here during the DMF reflux process. And we're hoping to achieve construction of the MOF and layered below and above of reduced graphene oxide, because of course the next step will be the addition of the palladium catalyst through palladium nitrate. Here by reduction, you can use typically microwave reduction for this process. So we end up incorporating palladium nanoparticles within the MOF and also within the reduced graphene oxide below and above the MOF crystal structure. So the reactions that we, of course, there is some characterization here. I'm showing quickly to show that the XRD of the cerium-MOF and the hybrid structure are not changing. This you can see here. And in this case, the middle pattern is 12.5%. This is optimized number or optimized ratio of graphene oxide in the hybrid structure. This is what we found to be the most active support, this kind of 12.5%. After that, we cannot get better properties for the support. Raman spectrum shows also combination of the cerium-MOF pattern and the graphene oxide or reduced graphene oxide because we're doing a reduction process here, and this all appear in the hybrid structure. All the peaks that belong to reduced graphene oxide and cerium-MOF appear in the in the hybrid structure. Similar FTIR shows the combination of the peaks related to graphene oxide and the peaks related to cerium-MOF in the hybrid structure. So very much we can say that we have the structure that we intended to form between these two types of support, the graphene oxide and the cerium-MOF. Now we go to the reaction, and before this is the SEM and of the catalyst. This is within the cerium-MOF here, and here within the hybrid structure. So the first one, this is just the cerium-MOF, the palladium on the cerium-MOF, and this is palladium within the hybrid structure. And you can see the hybrid structure better in this next TEM image, where you can see layers of reduced graphene oxide in addition to the cerium-MOF crystals. So the idea of having hybrid structure based on the characterizations that we have appears to be working here. Now we look at the reaction, and this is much more, also more characterization of TEM, showing the difference between if you have only graphene oxide or reduced graphene oxide, you have palladium nanoparticles distributed around. And if you have the hybrid structure, you can see still have the graphene oxide on the background, and you see also the crystals of the cerium-MOF, and both of them containing two different types of palladium nanoparticles. To look at the reaction activity here, what we're seeing is the conversion of vanillin, which is in red here showing. So this is as a function of time. The vanillin goes down. Remember, we have two products. One is the product that's not desirable, which is the vinyl alcohol, which is the blue. And the desirable product is the methoxyphenol, which is the black. So if you use only the cerium-MOF, palladium on cerium-MOF, no graphene hybrid structure here, we see that most of the product actually goes to the vinyl alcohol, which is undesirable product, and very less product goes to methoxyphenol. If we use the graphene oxide as a support with the same amount of palladium catalyst here, you see even less of the methoxyphenol, and again, the major product for the conversion of vanillin here is vinyl alcohol. If you have a mixture of these two, just a physical mixture of graphene oxide and the cerium MOF here, you see basically what you see in these two additions. Just adding these two results, you see again very little of the final product, methoxyphenol, and most of the product goes to the undesirable product, which is the vinyl alcohol. However, if you have the hybrid structure, and this is the hybrid structure here that we constructed, you can see that the vanillin goes down, and although the vinyl alcohol is formed, but it reacted quickly in few minutes, and it starts to form the final product that we like to have, which is the methoxyphenol, and reached 100% within 200 or 250 minutes. So it appears that the hybrid structure is really working in producing and in the final product, which is the methoxyphenol in this case. So in this part, this is the first example. We can say that the partially reduced graphene oxide cerium MOF hybrid scaffold is active support for palladium nanoparticles for transformation of vanillin into 2-methoxyphenol, which is, as I mentioned, this is important value-added compounds that can be used in pharmaceutical industry and in many other chemical industry. And we believe that the hybrid activity, the good activity for the hybrid support is due to the incorporation of both the reduced graphene oxide, which leads to dispersion, well dispersion of the palladium nanoparticles, and also you still have graphene oxide in the hybrid structure, which has acidic properties, which is important for this reaction to accelerate the formation of the phenol. So that's the first example for the hybrid structure to solve the problem of weak support from the cerium MOF by itself. Second problem is the same reaction, is the vanillin, also hydrodeoxygenation, but now we move to a different kind of MOF, which we heard about it, is UIO66, but this is amine incorporated. So we use two amino fusidic acid with cerium nitrate, zirconium chloride, and to form this amino UIO66 amine structure. The important point here of having the amine in the MOF is that when you incorporate the palladium, this happens in acidic conditions. So the formula that you will have is NH3 UIO66 2 and the palladium Cl4 -2. So there is a strong electrostatic attraction here between the palladium ions, the cations, and the palladium anion, sorry, and the amine complex. And this, following the reduction of the palladium ions, can ensure that you have well dispersed and very small palladium nanoparticles within this MOF. And actually, this is what we see. We see very small particles that can be formed in this case, and only when we use the amine UIO66 that the palladium particles are between 1.5 to 2.5 nanometer, which is very small for such a reaction, and they are definitely incorporated, most of them, within the crystals of the UIO66. That's very much reflected in the reaction steps. So you can see here very different activity, where you see a very rapid decrease in the vanillin reactions, and followed by almost very quick formation of vinyl alcohol, and then disappearance to form the methoxyphenol as a final product. So we can reach actually within 75 minutes or so about 100% conversion in this reaction, which is definitely the result that we're looking for. The only problem with this support here, that it requires a relatively high concentration to achieve this result. So we'd like to go below 2.5 2% weight of the palladium in this support, but with 2% we can reach 100% conversion, and this is again attributed to the presence of amine in the UiO66. The last reaction here, or the last system for the same reaction, is incorporation of tungsphoric acid, which is H3PW12O40, encapsulated within UiO66 amine for, again, the hydrodeoxygenation of vanillin in water. So this is the solid acid, which is known as HPW, or tungsphoric acid, and it has very strong acid properties, and if it can be incorporated within the UiO66, that provides very strong acid sites, which is required for this reaction. So you can see with the palladium catalyst, you can achieve very high activity in this case. So again, this is some characterization which shows that we can actually load, you see the XRD here on the left, up to 5% of the HPW, the solid acid, within the UiO66 without indication of HPO crystal structure itself. Above that, above 5%, this is 5%, from 1 to 5%, you see very similar structure to UiO66. But when we get to 20%, you can see the structure becomes, shows several of the peaks from the solid acid HPW. Like this peak here and this peak here. So we actually, it seems like 5% is close to the maximum that you can incorporate of HPW within the UiO66. Same results, you can see it from FTIR, where you start seeing signatures peaks for the solid acid at higher concentration. So 20% definitely shows these 4 peaks frequencies which attributed to the solid acid and not to the UiO66. But below 5%, you have very much only UiO66 vibrational signatures. We measure the acidity of these MOFs as a function of loading of HPW, and again, up to 5%, we can get increased acidity, which with 5% HPW within the MOF, we can measure acidity of up to 108 millivolt. But above that, if we go to 20%, we measure higher acidity, as you can see here. But of course, this is 20%, and 20%, we already have evidence of having the HPW outside the MOFs and leaching out on the MOFs. So that's not a good composition to use. We have to maintain with the 5% loading. We look now at the reaction profiles, the time profile for the reaction, and you can systematically see that the product starts to improve by increasing the amount of HPW loading. So this is first one here with no HPW. You have vinyl alcohol is the major product, and the methoxyphenol is in the middle here. But as you go to 1% here, the methoxyphenol starts to increase, 2% starts to increase, and we have here 4%, but when we get to 5%, we have actually 100% conversion. So this is only 5% HPW, and we have 100% conversion, and this is the conversion, as you see, as a function of the loading of HPW. The important point here, as compared to the UiO66 MOF, that with the incorporation of HPW, the solid acid, we are able now to reduce the concentration of palladium catalyst from 2% to 0.4%. So this is significant reduction of the amount of palladium used, and with 0.4 palladium, 0.4%, we can reach 100% conversion within 30 minutes reaction time, with we can say 100% selectivity for the desired product, which is methoxyphenol. So that, the third example that I wanted to cover for the vanillin dehydrodeoxygenation, and I can include this part by saying that this, in the last case where we incorporated solid acid within the UIO66, very low loading of palladium catalysts can be used, 0.4 weight%, which is significantly low, using the tungsphoric acid encapsulated within the UIO66, which shows very high activity. And this is actually considered the highest activity for this reaction ever reported in terms of the concentration of the catalyst that we use. So the results here definitely illustrate or the promise for the MOFs in creating unique support for challenging reactions. This vanillin dehydrodeoxygenation is one of the challenging reactions, and the MOFs appears, modification of the MOFs by incorporating the solid acid appears to solve this problem. So I go now to my next topic. And this work is formation of cobalt-copper bimetallic MOF, which as a catalyst, not as a catalyst support, which actually we show that it can outperforms the platinum carbon benchmark for oxygen reduction reaction. This work we did in collaboration with Lewis H. Goin from University of Texas, El Paso, and I'll show you the results. We did in my lab the synthesis of the bimetallic MOF and the characterization, and in H. Goin group, they did all the electrocatalysis work reported in this paper. So the objective, as I mentioned, of this is to replace the platinum catalyst, because platinum carbon is known as the benchmark for oxygen reduction reaction, which is very important, of course, for fuel cells and for many other metal battery, air battery, like zinc air battery. This reaction is extremely important for any electrochemical energy conversion, as I mentioned, including the fuel cells. The problem with the platinum catalyst, which that they have several drawbacks, including, of course, low abundance, very slow kinetics, and very high cost, and that limits, and everybody's trying to get away from using platinum as a catalyst for this reaction and for also other reactions. So the goal here is to find a replacement that does not use any precious metals, and the idea came to construct the cobalt-copper bimetallic framework and to use it as a catalyst to see if it can compete with platinum catalyst in this case. So the structure here is made with copper and metal, copper and cobalt bridged by oxygen. So it's a metal oxide layer forms of copper and oxygen and cobalt. And then we have two types of organic linkers, the BTC, which is the benzene tricarboxylic acid, and BTA is benzene tetramine. So these two ligands or two organic linkers are connected in layers above the oxide layers. So we have a bimetallic oxide layer that's blue and red here. Above and below, we have the organic linkers, which can be BTC or BTA. Different crystal structures were calculated with different Mohr ratios for between cobalt and copper. You can see here 1:1 and 2:1 and 3:1. And the experimental value, the measured XRD, and the calculated one for the 1:1 structure is shown here on the right, and it actually agrees with the calculated structure within 97%. So we are very confirmed that the calculated, the measured XRD corresponds to the 1:1 crystal structure, Mohr ratio of cobalt and copper. X-ray diffraction, we can get information and TEM and on also the morphology of the crystal. So we see that this belongs to triclinic morphology with average crystal size of 500 nanometer. And the cobalt copper distance lattice fringe is 7.15 nanometer, which corresponds to interplanar separation with transition metal nodes in this type of frameworks. And also the electron mapping, unfortunately, is not showing very well here, shows that the structure has very well distribution of cobalt and copper ions throughout the framework. It's very important to look at the XPS here because we can see evidence, clear evidence of electron density migration, which becomes very critical for the oxygen reduction reaction. The electron density moves from copper to cobalt and through the oxygen bridge. And you can see that if you're looking at the 2p copper 2p electron. So you can see that in the monometallic, which is the red monometallic copper, the XPS shifts into the bimetallic, which is the black here, toward higher energy. So when the XPS peak shifts to higher energy, that indicates electron deficient because the copper transferred electron density to the cobalt. This is exactly the opposite you see for the cobalt. So for the cobalt, you can see in the monometallic that 2p electron is at lower energy, binding energy, but in the bimetallic, it goes to higher binding energy. And so that indicates that there is electron density shift from copper to cobalt. You can also look at the FTIR and see that the coordination in the bimetallic system with both the carboxylic acid and the CN groups shifts to higher frequency. And this is shown here, which indicates, again, better coordination between the cobalt and copper and the organic linkers here. In the TGA analysis, we see also in the bimetallic there is shift to higher thermal stability. This is the green pattern here. There are 5 different steps of weight loss, but it's in all they are much higher stability than each of the individual monometallic MOF. Now, in the electrocatalytic activity, we're showing here the current density generated as a function of potential versus RHE standard electrode potential for hydrogen. And you can see that this is the black one is the bimetallic, the copper bimetallic MOF. It's actually has the highest current density profile, the black. The next is the red, is the platinum on carbon, and then the individuals copper. This is copper foil, the blue, and then we have the green is basically the 2 linkers, BTA and ATC, and the yellow here is the cobalt individual or the cobalt monometallic MOF. So it's clear that the bimetallic exceeds the current density that can be achieved by the platinum carbon. In the cyclic voltammetry here, you can see also well-defined cathode peak for the black here, black cycle, for the bimetallic MOF, and it's significantly higher than the platinum carbon one, which is in red here. Actually also the current density, but this one was done at 0 rotation, 0 RPM. This one is, this measurements here on the right is done at 1600 RPM, which is standard recommended by DOE for these measurements. And again, we see a shift, significant shift of 40 millivolt toward higher potential for the cobalt copper bimetallic compared to the platinum carbon. You can look also at the mass activity current per mass. As you see, the bimetallic has a much higher activity than the platinum carbon. You can also calculate the number of electrons that's transferred to each oxygen molecules. And in the bimetallic system, we get exactly 4 electrons, which forming the hydroxide ions. And that's not the case for the platinum carbon system. Finally, you can see in the terms of the recycling and the stability that the bimetallic has 99% stability, higher compared to the platinum carbon, which only achieves 75%. So these main points again, that bimetallic cobalt oxygen copper BTC BTA MOF electrocatalyst substantially surpass the electrocatalytic activity of both the monometallic copper and cobalt, and also platinum, and also like copper foil, other catalysts, and of course the platinum carbon, which we said to compare with this bimetallic. And the cathodic peak, as I mentioned, from cyclic voltammetry in oxygen saturated conditions is observed at 0.84 volts, which higher potentials by 50 millivolts than that achieved with platinum carbon system. And as I mentioned again, in the full 4-electron process to form the OH radical indicates that there is no intermediates that formed in the hydrogen in the oxygen reduction reaction, and that indicates that there is no undesirable intermediates that can be formed, and the kinetics it's much faster compared to the platinum carbon system. So in conclusion of that system, the catalytic properties of the non-precious cobalt copper bimetallic MOF surpassed that of the oxygen reduction reaction, the catalytic activity of the benchmark platinum carbon in terms of onset potential, half-wave potential, electrochemical stability, and that actually considered now the best non-precious oxygen reduction reaction catalyst reported in the literature. And we believe that the reason for this high activity is having the cobalt copper electron transfer process from copper to cobalt, which produce highly active catalytic sites for the oxygen reduction reaction, and the well-dispersed oxygen bridged by metallic centers in a porous framework connected in 3D framework improves the catalytic rates. These interactions, we believe, leads to lower energy barriers for intermediates in the catalytic process and the increasing oxygen reduction reaction catalytic activity. So with this, I like to thank students who did most of this work and the funding agency, and thank you for your attention.
Thank you very much. That was a really, really exciting talk, and what looked like some really remarkable catalysts as well. So, do we have any time? Well, sorry, do you have time? Do we have any questions, rather, from the audience? Either from as before, there are 2 microphones in the middle. While people are standing up, I had a question which perhaps might be pretty stereotypical for me. In your UAO66 amino systems, Do you see any effective defects? Is this something you've explored? Does this help or hinder any of the catalytic activity? That you
For the amine system?
Yeah, the UIO66 amino.
Yes, for the amino. We haven't actually looked for the defects, but the crystal structure appears at least similar to what's reported in the literature for that system.
Yeah, absolutely. It's one of the things that I think can sometimes help. So, and if they're at low concentrations, you don't see them in the powder at least. So perhaps something to explore, I guess. Oh, and we have a question. Go ahead.
Can I ask here? Yeah.
Oh, yeah, sorry. With the micro.
Sorry, please go ahead. Please go ahead.
I think it'll be switched on by the tech team.
It's on now. Thank you, Samy. Excellent talk. What are the prospects of using your catalyst in continuous flow?
In continuous?
Flow.
Yes. This is, of course, once you can reach, that's why the point of trying to use the lowest catalyst concentration becomes important to determine. So once you can reach a reasonable value, you can see that the flow system should work. So, but we have not done any of this in a flow system. But of course, definitely that's the trend. But you can, it's not, of course, wise to test that if the catalyst concentration is, you can calculate and find out what will be the desired concentration to have a flow system.
And the other challenge is to avoid leaching.
Yes. Of course, that's why this is also related, like for the hybrid structure or for the solid acid incorporation. This is related to exactly how much you can incorporate, so to avoid the leaching, because with higher acidity, you can have probably higher catalytic activity, but it will involve definitely significant leaching from the acid.
Thank you very much.
Hi. So very nice talk. So I was just curious when you had this bimetallic thing, copper, cobalt, you said that the charge transfer between the two is probably responsible for the high catalytic activity. Is there any design principle? Can one think of any other pair of bimetal? I mean, since you mentioned of this.
Yes, you can actually extrapolate, or based on this observation, we did not know that before that copper in the bimetallic will be transferred electron density to cobalt. But if this principle works here, you can, of course, look at other transition metals, and but providing that all other aspects will be valid, not just the electron transfer. So like the linker, the structure itself, so all of that. But yes, I think this is actually one, I believe, of the important results here, that electron transfer definitely in that direction improves the reaction efficiency.
Okay, thanks.
Oh, very nice talk, Samy. So apologies in advance, because I don't know much about catalysis, really, but we're working with some chemical engineers and chemists to develop nickel nanoparticles, tiny nickel nanoparticles on perovskites for catalysis. So I'm just wondering how the
For what catalysis?
Well, for CO2 reduction, things like that, high temperature, and also for anodes in solid oxide cells. So I'm just wondering about the performance of your materials compared to those systems, so transition metal oxides with nickel nanoparticles.
The problem with nickel nanoparticles, I don't know how you making the catalyst here, is of course the tendency for the oxidation. So maybe the bimetallic could be useful here.
Okay.
But we have not experienced much with pure nickel, because the oxidation also becomes a serious issue here.
Okay. Thanks.
So can you comment on the structural stability after the addition of acid in NH2 UiO66? Like MOFs are generally not chemically stable in chemical environment, so could you comment on that?
On the HPW.
Like yes.
Yes, yes. Actually, we didn't have to do much of thermal stability testing here, but within maybe up to 90 or 100 degrees, we see full thermal stability for the incorporated HPW with the 5% loading in the UiO66.
Like if we add more amount, like let's suppose 20 to 25%, there could be structural deterioration also.
Yes.
In the structure of MOF.
Yes, we cannot, we definitely see leaching and instability with 20% solid acid within the UiO66. But with the up to 5%, we see no evidence for reasonable thermal stability. We didn't even have to heat up to 100 degrees, but there is no leaching. And we determine this by acidity measurements and also by looking at HPLC and ICP measurements. So we can prove that this is the case for the low loading.
So like 5%
I think perhaps we
is
could
the
continue the
optimum
conversation
amount.
in the lunch break, just
Yes.
because in the interest of time. Thank you very, very much. And thanks again,
Thank you.
Samy. That was a fantastic